it's the time has come now to talk about curvature tensors, which means more physics, and geometry, and also a little bit more indices.
More indices.
So what is the idea? So we talked. Okay, so what are the things that we covered the other time? Right? We talked about if you have a Coulomb algebra, then you can equip it with some structures, namely a G, which was an endomorphism that was symmetric and squaring to the identity, symmetric. And there was a Hall density. I think we probably we introduced this notation. Yeah, we introduced it. No, I think we called L. The Hall density, invertible, so everywhere non-zero. So these two pieces of data were the ones that in physics corresponded to the bosonic part of whatever supergravity or something. This thing incidentally means that we had an orthogonal splitting of E into V plus and V minus. So V plus orthogonal is V minus. And then we talked about connections, where we differentiated the section along the other section. This was subject to some connection axioms. Also, we asked this to preserve the pairing on the Coulomb algebroid. Bracket, pairing on an anchor. And then we discussed what it means to be torsion-free and what it means that it preserves G and sigma. And we defined Levi-Civita connections. So we said that D is inside Levi-Civita class, which is sigma. This meant that this was 0, this was 0, and the torsion one lemma that, or like one remark that we had was that the equivalent characterization is that this means that if you take the covariant derivative of any section of V plus, then this preserves V plus. Preserves the space of sections of V plus. And this thing was equivalent to saying that the divergence associated to D, which is none else than the trace of U was defined to be the trace of the U. And then we had another divergence associated to sigma, which was the Lie derivative. Lie derivative. And this condition says that these two divergences have to coincide. And then there was a theorem that we proved, which says that this class is actually non-zero, non-empty. Okay, so now what do we do with this? So yeah. So the idea was that this space, unfortunately, has many. Sorry, non-zero.
Sure.
Non-empty. So the thing we didn't show, but I'm claiming is that this is actually a big space. So it's affine over section of some bundle. So this is big. It's large. But if we have an element in there, but let me say it like this, there are certain parts, matrix element of any connection in here, which are independent, of the representative. And G and sigma. And we can use this to build stuff. And we can build stuff out of them. Okay, so what does this mean? It means that, yeah, it means this. So there is like, if I, the condition of being inside here, it actually, there is a freedom in choosing representative in here, but it turns out that all of them have something in common. And we can use that common part to build something out of it. So
what do you mean by parts? Is it like subspaces, or is it like?
I mean, I will make it precise. Yeah, that put in quotation marks. Like there is some operations that you can build up of this, which are actually using. So, for instance, I will discuss three things. So, first one, let's rephrase this proposition. So for any, for any representative, we have. Maybe I should have. Okay, sorry. Let me insert here a notation. We will denote the projections onto these two guys. Projections, or the projections onto v plus minus by the corresponding subscripts. By the subscripts plus minus. So what I mean is that here, so u plus, I mean, I'm adhering to that notation, but I'm also just, in other words, okay, so all u plus into plus, all v minus into v minus. So if I take elements in there, then this thing is the same as taking the bracket and then projecting to the minus part. And similarly, the other way around. If I use the same two guys, let's say v minus u plus is v minus u plus projected to plus. Okay, so what this thing says that, well, I don't know in general how these connections act on arbitrary sections, but I know that if I act with something in u plus and something, if I act on something from v plus on something in v minus, I know what the result is independent of which representative I choose there. And the proof of this is, why it is true? Well, this is very simple. It just says that one has to remember what the definition of torsion was. If I take two sections, then this was dv minus dvu minus the bracket plus du v. So the proof of this, I will prove the first part, the second one I will notice. Well, we know that torsion is 0, so it's 0 in particular if this is in particular 0. So I can pair it with something. So this is again a section of the Goran algebroid. I can pair it with something, and I choose that something to be in v minus. So this is in section v minus. And then I just look at the definition. And what does the definition say? This is the same as u plus on v minus paired with w minus v minus u plus paired with w minus u minus u plus v minus paired with w minus and the last bit v u plus v minus, and pairing this last thing with w just means the W. I'll put it here. So that should be correct. So now the observation is that well, two of these terms vanish and two of them will give me what I need. So does anyone see any terms which are vanishing? Using this property, which I can. This is equivalence. Both of them vanishing. Okay, so here I'm differentiating a section of U plus, so I know that the result will be in V plus again. So it's orthogonal to V minus. So this is 0. For same reason this one, I'm differentiating something in V plus, so the result is again in V plus, so it will be orthogonal to this one. So what I'm getting is that, well, so I know that, okay, should I write it? So let's say,
And that was the condition of relativity, that thing.
the torsion frequency, yes, that's relativity in these three things. Vanishing of the torsion is among them. So what does this thing? So you know that this thing here, you're acting on something in V minus. So you know that this thing is in V minus already. This thing will have a V minus, but also a V plus part. But by pairing it with this, only the minus part survives. So in fact, here I can just as well put a projection onto minus. So then the part vanishes. And now I can just compare them. I have a section of V minus, another section, and I know that they pair the same, which means that they have to be the same. End of proof where I change the color in the middle. Okay, so this is one useful fact. Then there is two more operations. One of them is kind of silly. This just says that for any V, I'm not even writing it as a proposition because it says that if you take the trace of D2, which if you remember in our index notation this was the same as this. Well, we see in here. This is given in terms of sigma. So this is given in terms of divergence for sigma. So in particular, we see that the right hand side doesn't depend on the representative D, which means that the left hand side doesn't either. So the trace of the connection is actually, trace of relationship with the connection is actually uniquely fixed, irrespective of which D you choose, similarly to this property. The first property tells us that this kind of cross connection is determined. This one tells you that the trace of a connection is determined. Okay, this thing follows. First one follows from torsion freeness and from this one. This one. The second condition follows from this condition. Will be sigma equals 0. Okay. And there is a third thing, and for the third thing, I would need to. We haven't talked about spinners yet. We might later on, but for kind of ideological purposes, it's kind of good to say them here. So I will just say the words. So there is a. If you use this connection to construct the so-called Dirac operator. Specifically noted B slash. This is an operator that acts on spinners, on sections of the spinner bundle with respect to So we haven't talked about spinners, so we won't need to know, I won't be using this, it's just kind of it fits into this picture, and I want to say a few words about this, and then we'll go back and not use spinners, maybe reach them later on. But before defining the curvature tensors in the way that I'm going to define them, I wanted to kind of sketch an approach which might be conceivably ideologically better, and that goes via spinners. Okay, so just there is an associated bundle to this provides some topological conditions are satisfied. It's called the spinner bundle. It's a vector bundle. You can have sections of that. And there is a natural way how for any connection you can let that connection act on the spinner bundle. That's what it's called. And the claim is that this is also this is independent of the representative. Okay, so if you don't know much about spinners, don't worry. This is more of a this is just a sort of remark that I wanted to mention, but we will, in the end we will define things differently, not using the art. But I think it's good to mention it here. So
sorry.
Yeah.
If E is just Tn plus Tn T star n, is that the usual spinner bundle, like with respect to Tn?
It depends on what is V plus. So if we typically in all the applications that I know, if you want to really stick to some physical, and you want the V plus, if you take the anchor map and restrict it to V plus, it goes here, then it doesn't have to be, but it's good to impose that this is an isomorphism. And in that case, those would be the usual spinners.
Okay.
But you can do things more generally. There is some interesting cases where you don't apply this, and in that case, it's not. Yes, so the moral is that most often, yes, you can identify them as spinners there, but it turns out to be better to not do that, and instead treat them as living on a different bundle. In particular, in like type 2 supergravity, there is like left and right-handed things coming from string theory, and there you will have spinners both for V plus and for V minus, and it's kind of it is this kind of insight from generalized geometry which tells you that actually if you see these two sets of the Latinos and Gravitinos, or the relativity gravity, if you see them as not living both of them here, but one of them living here and then one living here, then actually that kind of simplifies things.
Okay.
So it's arguably more natural to consider them as living here and here instead of living here.
Okay.
Thank you. Okay, so just to finish this remark part, so okay, so the idea is that I can combine these three operations. Yeah, can combine these operations to build curvature tensors.
So what are the operations?
Combine these these three parts of the connection which are like okay, I will show what I mean. So I mean, like, yeah. So I want to build a curvature tensor. I want to use the connection for that, and I want to use it in a way that the only combinations of D that will ever appear will be either plus acting on minus, minus acting on plus, trace, or a Dirac operator. I only want those things to appear in the expression.
Why?
Because then I know that the resulting expression is independent of the choice of Levy-Chilton connection. So examples, let me learn some examples. So let me say what I mean. So we have these two subbundles, and I will now just this is my favorite notation. I will denote one of them with frame there with Greek letters, with Latin letters, and the other one with Latin letters with a dot. And together these things form a, if I take the basis, this is an adapted basis for these things. This thing I will call E alpha. Just to separate plus from minus. And then one can define the Ricci tensor. Yeah. I will call it RC. Generalized Ricci tensor. To be by this kind of trick. This this uses this index notation that we more or less successfully introduced the other time. And you can define a scalar curvature by saying for all spinors with respect to V plus. So it turns out that we can make this good. It turns out if you do this, if you take this particular combination where what I mean by that is the explanation. This is just a shorthand for well, the only thing that it can really mean.
C plus, then gamma.
Oh, V plus, sorry, I just, okay. Yeah, sometimes, okay, sorry, I just recently started using C plus.
C plus plus.
No. Yeah, so the strategy here is that, okay, without going into too much detail, this is what I was kind of heading for, that the expressions that appear here are, for instance, in the first thing, you are, so remember this is the index notation, it means that you hit U twice with a D and then it looks at the components of that. And in particular, the first thing says that you are making a trace, so that's well defined, that's number 2. And then you are taking a dot, like a minus derivative of a plus kind of object, which is also well defined by point 1. And the same thing here. You are either taking a trace or you are taking the derivative of two things which live in the orthogonal subbundle. I'm not saying it's immediate, that fits in what I was saying, but if you, for instance, work and I don't know, if you just decompose this in Christoffel symbols or something, you will see that actually it can be that it's unambiguous. And the same thing in here. There is a part where there is this mysterious Dirac operator that I didn't talk about much, which hits this thing. That I said is independent of the representative. And also the second thing is that this is a spinor with respect to V plus. So acting on it in a V minus direction is kind of fine, and that using the first step or its extension to spinors. And similar to this one, it also uses the trace. Okay, sorry, I'm realizing it's a bit more sketchy than I intended, but hopefully the idea is more or less clear. They can extract some independent parts of these operators, and then you can use them to construct something. So this is one way to do it. This is how it's done sometimes in the literature. But if you are confused about that, then you can forget about that, because now I'm going to do things differently and use a different organizational principle which doesn't involve spinners. I just felt that it would be a shame not to mention this, especially because it's a very word and we can put it maybe in some lecture notes or something. Yeah, maybe the analogy I should say that why these 5 particular expressions. So these two are analogs of some well-known expressions from Riemann and geometry. This green. So in the first case, there is an expression in Riemann and geometry that says that if you take a Ricci tensor and you act on a vector, I don't know, V, then this is, you can use Ricci with that connection to there's a thing like this is called Ricci identity sometimes. So this, in a sense, can be taken as a definition here. The factor of 1/2 is inconsequential. This is proper important. And this thing is analog of something that in classical geometry is called the Lichnerowitz formula. So there's an identity which says that if you take a scalar curvature and you act on a spinor, multiplying the spinor, probably you can say the other way around. So if you have a spinor, a rho, and you hit it with this differential operator, square of the Dirac minus Laplace, then this thing actually the derivative parts cancel each other out, then what you get in the end is just multiplication by a function, and the function coincides with scalar curvature. So this is called the Generalised formula. And the moral is that this is the analogous expression is the thing that gives you a nice definition in this case. So
It's CZ. If not, it's CZ.
is it?
I would say so.
Can you check? I apologize if I messed this up.
It will go. Yeah, in Wikipedia it's CZ.
Oh no, okay, I'm sorry. Yes, can you, yeah. Please adjust your notes. Okay, now let's wind back and let's do things again and with more detail and in a maybe more slightly less random way. Okay, there is one thing I should say, and that is that this subject of generalized Riemannian geometry that we are touching upon, that one is, I mean, it's been around for a couple of decades, but it's still not developed to a satisfactory extent. So there is various ways how to approach these things, and it's not clear, at least it's not clear to me which one of them is the right way. I think none of them is actually the right way. It's like I think the right way is not yet properly understood. And each of the methods that I know, they have some disadvantages. Like the disadvantage here, well, apart from the fact that I would need to introduce spinners. So, well, this construction, if you believe me, this construction shows that the right-hand side at least is independent of the choice of representative of the Lev-Civita connection. But it's not clear, for instance, that the thing that it defines is really a tensor of quantity. It's not clear a priori that the derivatives here actually kill each other out and the result is algebraic. So that thing you have to show. And also, I don't know in terms of this definition, how I would easily show one of the theorems that I'm aiming for, which is the fact that the variation of the Einstein-Hilbert action is given by a rigid tensor. I don't know how to show it directly from this.
And it looks kind of asymmetric with respect to Gaussian and minus.
Oh yes.
So is it or is it just does it look like it?
It is asymmetric. It is slightly asymmetric. Yes. Yes, that's it. That's actually, yeah, very good. That's nice. I like that. Yeah, that's nice. Yes, good observation.
So then could you define the same thing with AA?
Yeah, so it turns out that you can swap the dotted and undotted indices. You can swap B plus and B minus. It turns out that this object stays the same, and this one changes slightly. It changes by a function, but that function is a weird function. It's a function which is independent of everything. It's independent of G, of D, of sigma. It only depends on the Courant algebra itself. So it's like, for every Courant algebra, there is a canonical function that you can associate to it, which is a very weird thing.
Does it have a name? What function?
You can call it the square of the generating Dirac operator.
Square of the?
Of the generating Dirac operator.
Okay.
So, no, it doesn't have a name. Yes.
But if it is like kind of invariant function?
Yeah, it's invariant under all the Courant algebra automorphisms, so in particular it's invariant under row of any, under anchor of any section. It's a weird thing. Yeah.
And does it have in like applications, like if you apply it to I don't know what you like, the string theory or whatever, does
well, okay, I should make it less mysterious. So this function for exact Courant algebra is 0.
Okay.
For transitive Courant algebra is where you have some Lie algebra. It's the structure is the kind of the structure constant, the Lie algebra constructed that is a constant function on transitive Courant algebra. Generally it's something horrible, but at least on transitive and exact case you know what it is.
So it's expressed in terms of like the Lie algebra in the case of let's say the
transitive Courant algebra.
quadratic.
Yes. Yeah. It only depends on the Courant algebra data. Yeah. Yes. So there is a slight freedom in defining the scalar curvature for Courant algebras. In particular, you can also take like the difference of these two things.
Or average, and that it should be independent of the.
Yes, you can do that, but then that won't satisfy Generalised formula. But in type 2, you actually want to have strict v plus and v minus symmetrically. But it turns out that in type 2 only works on exact chronology, where the function is 0 and everything. So there's some like, interesting subtleties in this story. Also, the fact that Ricci tensors are the same, that's kind of true if you work with half densities, but it's not true if you work with more general divergences. So the story is a bit subtle, so it shows kind of a middle, like particular trajectory through it. But yeah, good, very good. Okay, so now let's take a step back. Now let's make a definition. So let E over M be a coordinate algebraic, and let's choose a representative of the Levi-Civita class. Okay, this is a slick way of saying that we choose a G, a sigma, and a D, which is Levi-Civita. So now we can define the Riemann tensor. So the way I'm going to do it actually pretty unsatisfactory for different reasons, as you will see maybe. In particular, this Riemann tensor is not really a great object to have in this case. So what is this? So this is a thing that needs 4 sections. Okay, so this is backslash times. Okay, 4 copies of this, and it gives a function. And yeah, this is the point where you will see the most indices if you. Yeah, that's probably partly why it's not so. Not such a great object. Okay. I was actually I actually spent quite a lot of time trying to find the easiest way to present this. So, in case you for some reason are not fond of this index notation, you can use one of these formulas that we sketched the other day and rewrite it instead without this abstract index notation. It's a slightly longer expression, but W plus the same expression where you exchange these pairs. Plus where I need to trace over these two things. So let me insert here a frame.
So when you write those exchanges, is it altogether 4 terms or 3
No,
terms?
two terms. I really mean you exchange. Yeah, sorry. You exchange x, y with z, w.
So only 2 terms in total.
Yes. This is a thing that makes the Riemann tensor symmetric with both. Yes, I'll have to comment on why this random expression. Well, if you look at, if you would define, if this would be ordinary, if this would be Riemann geometry and you would have Levi-Civita connections, not plus instead of these, then this is maybe up to some sign and maybe factor of 1/2. The first expression that you have here is what you would use to define the Riemann tensor. It turns out this doesn't work. It doesn't produce a tensor. It's because this bracket is weird if you try to get, this bracket is not a Lie bracket. It behaves differently when you multiply entries by functions. So yeah, this is just not a tensor. So it turns out that the only way I know how to correct it is that you just you symmetrize it manually in these two things, and then you have to add a weird correction term to make it work. This is a very unsatisfactory tensor. If you think that, then I agree with you.
It's a bit strange that you write it down as WZXY.
Yeah, that is
But
also.
then you exchange XY with ZW.
Yeah. Yes, I know. Yeah, you have a good eye. Yes.
So is there a satisfactory?
Well, you can rename those things. I don't remember why we defined it like this. So there was some underlying reason which I forgot. Also, it's under the alphabet. Well, I know. It's not very good. It's part of what, yeah.
Wiggles in the dark.
Yeah, very good. Exactly.
Is there
Maybe I
like,
should turn on the light.
is there like nice Riemann tensor that you
No, there is no Riemann. Okay. So this is slightly. I would argue that this is slightly nicer to write it without this, because then at least those two pairs of these two things are at least shrunk into one expression.
Well, I mean not formula, but like object if there exists.
So I don't think so. So the thing with generalized geometry is that there is I don't want to claim it as a theorem because I haven't seen or made it proof, but there is like, let's call it the meta theorem. That there is like no Riemann tensor in generalized geometry. There is always something you lose. You either lose tensor reality if you do the thing that you naively want to do. This thing looks like a curvature operator. No. Oh, okay. So yes, it does, but it's not tensor. It's not tensorial because of x. The way functions get out from this one is weird. So there is. This is the closest approximation to a meaningful object, but this is still very far from meaningful. The reason I'm doing it is that this presents a way to kind of derive uniformly the Ricci scalar and the Ricci tensor and scalar curvature, and also allows you to see why varying Einstein-Hilbert action you get the Ricci tensor. There was quite a lot of inner discussion with myself about doing it this way. I don't think this is ultimately the way you want to do. This object is bad. Like you don't want to work with that typically. There is no, and the reason I believe is that this thing is kind of ultimately tied up with string theory in one sense or another, in one part of the story, which is kind of the thing we are following, it's tied up concretely with supergravity, and in supergravity, or even with worldsheet, you can do the worldsheet description as well. But both of these things, if you look at string theory textbooks, the only thing that arise are the Ricci tensor and the scalar curvature. You never see a Riemann tensor explicitly unless you go to higher corrections in which you need to do something else entirely. So
Something else entirely.
You need to do higher corrections.
Okay, like
High derivative corrections, alpha prime and G-string corrections and all these kind of things.
But like in ordinary Riemannian geometry, Riemann tensor kind of measures if you know the commutator co-indexes, so how it is not flat. So
Yeah.
there is no such thing here.
No, but here even the connections themselves are weird. Like this is not like actually I should have already said like the connections themselves are very unsatisfactory. So the things that are true are these G and sigma. So already the fact that there is not a unique with a connection means that it's sort of like a red herring. That you should really, if you want to work with it, then you should either do one of these tricks that you only work with parts which are well defined, or you should just avoid doing that and just write everything in terms of these things directly. You can do that. That's another way to do things, by the way, but that one is unsatisfactory for different reasons. That one is just a random formula which doesn't. I don't know. There must be a good way to present this, but I don't think I don't know of it, and I suspect it's not what the minimal effort way is. Sorry, I forgot the question. Oh, the Riemann. Yeah. So that we have to say that these connections are not great objects. So their flatness is consequently also not. Good. Okay, so now I'll use this object for, let's prove something about it, which is the part where we'll use a little bit of indices, but then, and then we use it to define Ricci tensor and scalar curvature as contractions of this. That at least works. So there is proposition, this is a tensor. I.e. Riemann D is actually a section of the fourth power of this. Remember that E is identified E dual because there's a pairing. And and this has the following symmetries.
So is there a reason why before you used times and now all times?
Yeah, because before I didn't know it was linear by linear. This is really like tensor.
So by all times you mean like C infinity linear, and before you meant just like R linear or whatever.
Yes. C infinity linear. Yeah, before I was just it's like a Cartesian product of two things. You know, it's like R quadrilinear. Okay. But here we want to show that there's a tensorial. And it has the following symmetry, so the claim is that this has the symmetries as the usual Riemann tensor. It's a bit puzzling, given that I just told you that this is a bad object. First of all. Okay, let me write it like this and then let me ask if you understand what I meant. Alpha, beta, delta. This is how you usually write these things in physics. Let me check. Okay, so are you familiar with this notation? Like, what does this mean? This is a anti-symmetrization. So the first thing it tells you that the Riemann tensor, if you anti-symmetrize it on first two indices, you get back the Riemann tensor, which means that it's anti-symmetric on the first two indices. Okay, so this is equality here means that anti-symmetry in alpha beta. Similarly, this thing tells you that it's anti-symmetry in gamma delta. And well, this is the fact that if you transpose, if you swap the two pairs of indices, it's the same. So those are the symmetries that you have in the ordinary geometry if you work with.
The last one is something like a Bianchi identity?
Yeah, this is sometimes called the algebraic Bianchi identity.
But is it, I guess it's true also for cyclic, because of the anti-symmetry can do?
Sorry?
Is it true also if instead of complete anti-symmetry? I guess so, no? Because it's anti-symmetry.
Yes,
You write Bianchi as cyclic thing instead of
Oh,
complete
okay. You know, it's the same because it's anti-symmetric. Also, this is equivalent to anti-symmetrizing on all four indices.
Right.
It's zero, sorry. If you that follows from representations of the symmetry group. Yeah, anti-symmetrizing also in the ordinary case. On three, anti-symmetrizing on three and four indices is the same as the consequence of the other things. Some magic with the anti-double or something. Okay, so let's prove it. I will prove that apart from the last one, which is kind of a nasty proof, and I don't know what a good way. But we won't need that anyway. So, okay, let's start by a little bit of practice with this index calculus. Let me persuade you that this thing is a reasonable thing to do. So, if I have two tensors, I put the indices out, but it doesn't really matter for now. So if I have two tensors, so there is some indices here, some other indices, and I take the derivative of this, and the first claim is that this satisfies, well, like this. I mean, this might be obvious, and it kind of is, but I think it's good to realize that it's true. So, this kind of index calculus, whereby the meaning of expressions is that you hit it with whatever number of these you have, and then you take a component in the end, which keeps everything tensorial. It's good to know that this thing is still kind of satisfies the usual properties that you want to have. In this case, this follows from the definition. This means that you take the tensor product of this object, tensor product of this and this, you hit it with D, and then you look at the component, but D satisfies Leibniz, blah blah. That's what it is. There is nothing too deep about this one. I'm including it as a first step.
So what is new about this one? I mean,
Sorry?
D is just kind of square derivative, so why is this new? Or isn't it?
It's not really new one. This is why I'm thinking is a lemma. It's a consequence of the fact. It's an immediate consequence of the fact that if you would take this thing, then it satisfies this thing.
Yeah.
X. It's not supposed to be non-trivial. It's this, translate it into this language. But in this case, the translation is immediate, so that's why it's immediate. Maybe I should have not. Yeah, maybe it would be better to not include this one. Never mind. Let me include the second one. I guess I just want to stress that what's happening here is potentially slightly non-trivial, but in fact it's not. Maybe that's not a great thing to do. Well, in any case, yeah, this is again similarly confusing and trivial, but anyway, it's the fact that the commutator preserves the commutator of two such objects also acts in a Leibniz way. It's a consequence of the fact that commutator of two covariant derivatives is a. Wait, is it true there even? It's not even true there, is it? No, it is.
True. Yeah, I mean, so.
Yes, true. Yes, sorry, yeah, it's true. Yeah. Sorry, I'm making it confusing with non-trivial, but that's okay. But yeah, this is kind of follows as in the usual case, like simply writing this as d alpha d beta minus d beta d alpha, then hitting these things and you're seeing that the cross terms vanish. So there's nothing terribly exciting. Okay, so let me do the last one, which is at least a slightly non-trivial thing. So this one, the last one, uses torsion freeness. The other ones don't. Other ones are, this is general. Any D. This one uses the torsion. So let me show the last one. Okay, so what is the meaning of this equation? Like, this thing is still expecting to eat a section, so this is in fact, this is gamma E star. This is gamma E. Okay, so let me prove it in the sense of proving the last one, because the first two are not. So, now. So now we have two covariant derivatives. So we need to look back at these formulas of how to relate this to the other language where you have covariant derivatives with respect to some sections. And if you go back, then there is well, you need to look 2 or 3 lectures ago, and there was this formula which I am now anti-symmetrizing. Here I'm using the formula. It says u alpha b beta d alpha d beta on any object, t with some indices is du dv on t minus d du d on t, and then the whole thing. Applying this to a function, I get this thing. This is the transition between these two languages. Okay, and now, but since this is a function, we know how connections act on functions. They just use the anchor map. So this is just a commutator of the anchor maps of the anchor maps applied to the respective sections. And the same thing in here. This is duv minus dvu acting on f. Voila, voila. Here we use the formula that we know that the anchor intertwines the brackets. So we know that this is the same. So now we can put the anchors together. And we get uv minus duv plus dvu f. And well, by torsion, by vanishing of the torsion, this is duv. Okay. In general, this would be the torsion of u v minus. This is the general formula, but now we don't have the torsion. So that's the result. Maybe as heads up for the future, I would say that this is probably the most the nastiest proof that we will see, although it's not very that bad actually. Then it should get better. Although maybe I'm lying. I don't think I have. Okay, any questions? Any other questions? Oh, okay, so now let's go. Oh, the areas that we the remote tensor. Okay. Okay, this is painful. Okay, I did a trick which was logistically very bad. I erased the only formula that I will need. So while I'm writing it, you can lay back and relax. Or ask questions. Okay.
Okay, why are there only 3 indices when there are 4 inputs? Gamma is missing.
In where? In here?
Yeah, in this what you're writing.
What do you mean 3 indices?
Well, there is delta, beta, and alpha, but there is no gamma.
Yeah, but is that a problem?
Well, no, but
Yeah,
I'm just wondering why that is.
Yeah, well, you see some of them share the same index, like these two guys have the same index.
Yeah.
So,
But why did we skip gamma?
okay, so
For example, also.
I see, no, I like the question. Again, I don't remember why. Yeah, good question, maybe. I don't know, maybe I chose them to emphasize the fact that there is 4 things. You know, good question, I don't know. You got me there, I don't remember. Yeah. Okay, so now, fortunately, the proof is not that bad. So first, let's show tensor reality in one of the slots. So tensor reality in X. First bullet. What does this mean? Riemann d wz fxy minus f. So we want to show that this vanishes. This is what tensor reality means. So let's calculate it. So what are the first term? Here x is not hit by any derivatives. So the first term in here and in here will cancel. So fortunately we only need to look at the last two. And furthermore, we know that this, so we need to look at what happens if I put a function here. How does it go out? Well, there I use the second bullet there. So I know that in here and in here, the difference of this term will be this commutator acting on f. So x goes out, and I have d alpha d delta on f. Okay, so imagine that I wrote this term once with an f here, and once with an f out, and I subtract them, and by the second formula, the result is simply this commutator acting on f. So that took care of this guy. Here, well, a similar thing. If I put an f in front of x, and if I put f out, then the difference between them is this z acting on f. So minus x beta d alpha f d alpha z delta. Okay, now we show that this is 0. Yeah. I guess we can rerun. Why is this 0? So we can take x beta out of this. And here we have z alpha, and we know what this is. This is that. So, crap, okay. This chalk is getting smaller and smaller by me dropping it. So, I want to use the property that. So I need to look at here, find out the alpha index and the delta index. And I want to use that property there. So this is rho 1/2 y beta x beta, and then there is rho of dz and w, and this acting on f. That's the first term. Yes, that's right. What about the other one? Yes. So let me write the other one. Okay, let me put y and x together. Yes, and I have this one. And I have W with this guy. And put them, so just get them together. Okay. What now? Show this thing is the same as this, where I took the alpha part of that. So I don't know, I can put the alpha. You see that? This is the same. Good. So now I can put these two things. So this is also this one. I can, if I want, I can write it as rho, because on functions the connection ends simply by the anchor map. So this is the same. And these two things multiplied together, I can join them together, and I can say this is rho of dz w acting on f. Do you see that? I have like, there is one middle step if you wish. This is E alpha multiplied by a bunch of numbers, and the numbers are precisely these kind of things. Okay, so I put this thing inside the anchor map, because the anchor map is linear, and then this thing is the same as if I would erase the thing. And that's the same, and that, you know, I get the same thing twice, so it's 0. Good. So that takes care of the tensor reality in X. Fortunately, by construction, this thing is symmetric in exchanging X and Y with how do it go? Z and W? Something like this. X with Z, Y with X with Z. Oh, damn it. Exchange them, I have to relabel the indices, so I get X alpha, what the hell? X with Z, Y with W, yeah. If I exchange X and z, that switches beta and delta, so yeah, that works. And here, if I swap x with z, I will have, oh yeah, and I swap them, so I swap, yeah, it's fine. Okay, yeah, so you can, sorry, yeah, this thing, you have to relabel some indices to see it in the first thing, but it is symmetric in those two things, which means that's showing that yeah, so this thing implies, okay, that symmetry is x, y, and the w means that the thing implies tensoriality in z as well. Okay, so there is not much to do there, but for the last antisymmetry thing, antisymmetry in the exchange of, sorry, no, yes, tensoriality. Oh, yes, sorry. So yeah, so from the fact that it's written like this, you see that there is no derivatives hitting w and y. So we know that this is tensorial already in w and y. We now prove tensoriality in x, and by this antisymmetry we follow the tensoriality in z. So it's actually tensorial in all. So this is tensor. Okay, that part is done. The only thing that remains is to prove the symmetries. While already the symmetry in exchange of these two things is by construction. So the thing that we really need to do is just show one of the antisymmetries, and let's do the one where we swap x and y. Yes. So let's show the antisymmetry in x and y. No, w and z, sorry. W and z. Okay. So how do I do that? The easiest thing is just to take the Riemann tensor and put the same thing here and here. So antisymmetry is the same that if you is equivalent to saying that if I put the same thing in there, then this is 0. So let's calculate this. And that's the last calculation here. So if I put the same thing both for W and Z, there should be something that vanishes. So this thing. Yes. If I take W and if I put W and Z to be the same, then I can, if I imagine that I put whatever W here, then I have W delta, W alpha, so they are symmetric in delta and alpha, but this thing is antisymmetric. So the middle term doesn't contribute. So we only have the other two. The first and the last. Z, which is not W, delta, and the last term. We have d alpha x beta, and here we have d alpha delta. Okay, so now the trick is to realize that since we have two w's and this thing is a derivative thing, then we can write the first term essentially as we can put both of them together. I mean, we can put this one under the derivative. Okay, so I can write it as a square in a 1/4, putting this one next to the other one, and the same here. D alpha. Okay, what a great trick. Okay, so now the simplification now comes from the fact that now I'm acting only on a function. So this is a if I contract this thing, this is really a function. If you you want, there is an underlying fact which says that contractions commute with. There is some underlying fact. Well, these two things are functions, and we know how these things, how the derivatives act on functions. Namely, here we use the lemma to conclude that. We use the lemma to say that this is rho of dx y acting on this thing, technically just omega squared, w squared. And in the second case, I have an anchor map. Rho of rho e alpha acting on w squared. And by the same argument as before, I can write these guys together as d e alpha x paired to y, and I can put them together, and these I finally get that this is rho of dx y, which is the same as here, and hence this is 0. Okay, so now the claim is that this is all that we want, because from this it follows that, for instance, all the other antisymmetries apart from the algebraic Bianchi, all of the others follow. So, for instance, if you want to see that this tensor is antisymmetric in x and y, which corresponding to the last two indices. So how do I see that? So I have all usual stuff. So I use the fact that it's antisymmetric in the pairs of indices to swap them. Then I use the antisymmetry in the first pair, which we just proved. So this is minus Riemann delta gamma alpha beta, and then I swap them back the pairs of indices. So I get Riemann alpha beta delta gamma, which shows that it's antisymmetric in the last pair. And the only thing that remains to be proven is this algebraic Bianchi. This is harder. So I won't do that. I think you would probably.
Typically, just a consequence of Jacobi identity for deep brackets, but I mean here I don't know.
Yeah.
It would also be related to that. Or
It should be, yeah. It's the Jacobi identity for the current bracket.
Okay.
Yeah. The quickest way to show that is that I know is to break it to kind of Christopher symbols, which is not ideal. Yeah, there must be a better way. But anyway, fortunately now we are out of this unpleasant water, so now we can assume that we understand what's going on, and we can just find the other tensors using this thing. And that's maybe as much as we can do. Okay. So now we have a tensor which depends on G, depends on sigma, but it also depends a priori on the choice of the Levi-Civita connection. So now, but at least we have a tensor. That's something. So the strategy now is to take particular contractions of this tensor and show that if you do it cleverly, then those particular contractions in fact will be independent of the representative. Will only depend on G and sigma. Yeah, any questions in the meantime? Where is the one? So I guess in some sense you can say that in the generalized geometric version of the Riemann geometry, there is in some sense, like this Riemann tensor is sort of much bigger. It contains things which are not nice. But there is, in some sense, if you look at objects that are meaningful in the end, which is the Ricci tensor and the Curvature, there is less of those objects than there is in normal geometry. So it's somewhat like more restricted environment. It's kind of strange. Okay. So now we have this Riemann tensor. And so now we can define finally these objects that we are after. So it's now a Levi-Civita connection for this pair. And we define both the generalized Ricci tensor which I will call it RC, and this thing will be for us, again after some internal debate with myself, this thing will be an object which lives in this particular bundle. And we define a generalized scalar curvature.
Something really naive.
Yeah.
Not really an expert on this subject, but okay. So in this case, in generalized geometry, you don't have a unique Levi-Civita connection.
Yes.
But are there any like structural results of the potential Levi-Civita connections that you could take? Let's say, take a space of connections, and I don't know. Let's say, can you say something about the space, like some topological properties of the space? Could you find, let's say, I don't know, homotopies, isotopies of connections?
So the space of connections is affine over sections of subbundle. So it's the difference of two connections is a tensor.
Okay, so.
You can characterize how the tensor looks like. It's not very nice. It's just a bunch of. It has to be something that is in E tensor, and it has some symmetry properties. You can show that it's non-empty. So it's there is not a there is no preferred choice in general to choose there. But there is other things that you can do. There is at least something that we call a variation of uniqueness. So if you have a family of metrics, so if you study something like a family of these Hall densities, which kind of come together as a sort of a smaller cousin of it, and you pick a Levi-Civita connection for the zero for the time zero, then there is a natural way to deform it along this, which produces a family of Levi-Civitas. It's not super deep results, but at least there is some sort of handle that you can have. Like you can, in a sense, this says that the spatial Levi-Civita connection is some bundle. If you see that like infinite dimensional space of such structures, and over there is an infinite dimensional bundle with fiber given by Levi-Civita connections, and there is a natural connection on that space, which tells you how to deform things once you already started with something. So that is sometimes useful. So it's not completely crazy.
So you know how to follow the path of Levi-Civita.
Yes. Yeah. Thank you. Okay, so this thing will be a function on the base. And the way I define them is that I take Ricci. So we know that this has a 1b plus and 1b minus index. So remember that we said that there is frames labeled with Latin indices, and Latin indices in dot. So this thing will be the contraction of Riemann B, A, B, C dot, and a 4, just to make it more hilarious. It's unfortunate. It's the form, but what can you do? And similarly, this thing is defined like this. So remember, it means that I'm So here it means that I'm making a contraction, but I'm only contracting along V plus. And here I'm making two contractions, both of them along V plus. Okay, now why do I do this? This is a pretty random thing to do. So So why? So to justify these joints, contractions. Let me state this as a proposition. Let me not prove it because again, this is something relatively nasty, and we really don't need it. It's only entered in justifying this definition. So this is a proposition that says that okay, there is actually Riemann. There's some bits of Riemann tensor that are not as weird as you think. For instance, if you take a part of Riemann tensor which lives in V plus, tensor V minus, tensor V plus, tensor V minus, so something that has like plus minus part, and this is 0. That's one thing you can show. The other thing that you can show is that if you take this contraction that I would do here for Ricci, but I would contract this not along V plus but along V minus, then it gives the same thing again. These are not at all obvious properties, but they're true. So if I would do the same thing, but I would contract this thing on V minus instead of V plus, it in fact gives the same result. It's the second property. And the last one, the most bizarre, says that if I would do this thing, what I did here, but I would do it, I would put all 4 of them on V minus, then this is not 0, but this is this function psi that I alluded to before, where I said it doesn't have a name, so on the board has a name, it's called psi. So this is a function independent of G, of sigma, and of V. So it's intrinsically associated to the Courant algebra. Intrinsic to the Courant algebra. In fact, you were asking about the name. I think it's probably fair to call this thing a curvature of the Courant algebra. I might justify that later. But okay, so I'm not proving this, and this is just to state that there is a little bit of constraint in here. And so, for instance, so thus.
R in the.
Oh, R in it.
R.
Yeah, again, two notations. Sometimes I call it with R. You know, in physics, people don't usually distinguish notation for these tensors. They just write 4 indices or 2 or no indices. Mathematicians prefer to label them differently sometimes. RM, RC, and something else, R maybe. So thus, in fact, Ricci tensor I could have defined it maybe slightly less weirdly by saying that it's 2 times. So up to the factor of 2, which is anyway probably more palatable, more appropriate than factor of 4. You see that I could have just as well defined it as a Ricci is a contraction of Riemann along E, as you would normally define a Ricci tensor, you just contract it. But then plus we project the result onto V plus tensor V minus. Because note that in this contraction I'm specifying that I want this index to live in V plus. I specify that I'm interested only in the V plus tensor V minus part. I'm not interested in the cross part. In fact, they are not good objects. So this is just put slightly more explanation that I could have defined it more along the usual definition, and in fact it gives the same thing because of this equality. Now for scalar curvature, so you one could also try to define the scalar curvature as follows. So you can again follow the standard story geometry, and you could just say that this is a contraction. You do, you know, normal geometry, what you do is you take Riemann tensor, you contract it once to get Ricci, and then you use the metric to contract on the other two indices. So you could say that maybe this one is better as a definition of scalar curvature. So let's see what this thing is. And if we develop it, the claim is that it's more okay, the thing I put up there. So, okay, let me first put some indices up and down to make this more. G for the symmetric tensors, doesn't matter if I sort them. Beta alpha, beta gamma. Okay, so I only did the harmless thing so far. Now the thing is that this is the endomorphism G. So this is G. Remember that G restricted to V plus or minus was plus minus identity, which means that if the indices run over V plus, this thing behaves like Kronecker delta. If it runs over V minus, this behaves like minus Kronecker delta. So, what does this mean? It means that CA, Riemann, beta A, beta C, while it behaves as minus Kronecker delta on C minus, V minus. So, this one. Okay, so if I sum over, this is really Riemann beta A minus Riemann beta A dot. And now I can similarly this contraction along E, I can contract it, trace over E, I can write it as a sum of trace over E is trace over V plus trace over V minus. But for instance here, if I would do V minus, then using this first thing, I know that plus minus bits are 0, which tells me that in the first trace only the first thing will contribute. So this is really the Riemann of BA, and the second thing similarly is all things dotted. Okay, so the cross terms vanish because of this thing. And now, using the last property, I can essentially write this as 2 times the first guy. But unfortunately, there is also minus this sign. So the answer is yes, you could have defined a scalar curvature like this. It would be meaningful, but it would not. It would be essentially the definition that we put plus minus some function that is kind of silly, that is invariant under all the structure. So there is in fact this kind of unfortunate choice. You can choose to do it either that way or that way. After some thought, first I wanted to do it like this, and then I decided it is better to do it like this, but I think this is the one that satisfies better properties, like the Lichtenberg formula, for instance. I think for that one you need the other one. So, yeah.
Sorry, I didn't get why the Ricci is projected over V plus tensor.
Oh, I didn't say, no,
I know this
good.
is not something.
That's a very good question because I just ran out of the stuff I wanted to say. So the reason I didn't say the reason. So in principle you could say that you put like alpha gamma, and you could say that you have it defined as a section of E tensor E. But the big claim comes in the next lecture will be that these objects that I wrote them, this one and those two things, that they are actually independent of the representative of the Levi-Civita connection. So they only depend on G and sigma. So we will see they depend only on G and sigma and not on the representative here. That's the unsatisfactory answer, which the answer is that the other bits actually do depend on the. They're not good. They're like bad objects. They depend on the representative of D, so they are just as bad as the Riemann tensor.
Okay.
There is slightly more satisfactory answer, which says that, and that's connected to the theory of the Ricci flow. So we will see later on that you can define an Einstein-Hilbert functional where you use this scalar curvature, which depends on G and sigma, as we will show next time, and you can multiply it by sigma squared to get a density and integrate it over. So this is a functional of G and sigma, which you can call the generalized Einstein-Hilbert functional. So this is glimpse of the future. This doesn't need to go into the equation. What I want to say. So yeah. So if you now look at the space of all such pairs of G's and sigma, so you have this big space of fields, and you can then first claim that space, so there's like a big space of all possible pairs of G and sigma. First claim is that this thing has a natural metric. That's not super surprising. It uses the fact that, well, this is a metric sort of. Anyway, there is a natural metric on this space, and there is this functional, and you can calculate the gradient of that functional. So that will give you some. That will give you some vector fields in here, and in fact, and this is what you would call a Ricci flow. In fact, so that was part of our motivation of why we were doing this. And in particular, this kind of Ricci. So there will be a natural way to interpret this, and I forgot there is some number which I forgot, maybe it's plus minus. So the gradient flow will actually look like this, and the meaning of this. Okay, so this is a meaningful. Yeah. So it turns out that G, which was something like E, and it was symmetric, and it's squared to 1, and you can show that as a consequence, if you have a parameter, if you have a family of these things, and if you differentiate them, so you take this thing, then this thing will in fact, if you take the A, B part of that, or the A dot, B dot part, that those are 0, so the only thing that the tangent space of the space of metrics is given by that, B plus tensor B minus. So yeah, tangent space to the space of all metrics at the given metric, you can identify with the section of B plus tensor B minus. And that's why a Ricci flow is meaningful. So it's precisely the part that tells you how to deform the metric.
Okay. So we could have defined the full.
We could have
tensor, but the only part which enters the Ricci flow is the one that is invariant under the choice of the Ricci connection.
Yeah, the Ricci flow doesn't feel any Ricci connection. It's just an equation for these things.
Right.
Yeah. So I think find this. Yeah, I think this is the. So you want your Ricci to live here, and that's what you want. That's why partly. That I think is a better explanation.
Sure. Yeah,
But there's a pragmatic one which says that this just doesn't work if you do the rest. It's a bad object.
Why is it that? So
It
depends
on
on
T.
But it is a tensor.
It is a tensor.
Yeah,
Yes. But the guiding principle seems to be that the good objects are the ones which do not.
Sure.
Okay. Very